Welcome to the Token Engineering Podcast, a show about AI economics and the cost of thinking from Neurometric on the token minting movement, the discipline emerging to make every unit of AI work cheaper, faster, and more reliably. Today, we have an episode again with Yash and I. We're going to be exploring a really interesting paper. We've looked at papers on this show arguing that the bottleneck in small models is often not the training, it is everything around it. This paper says the same thing from the opposite direction, and it says it with the benchmark. So a 9 billion parameter model that lands close to Claude Haiku on hard terminal work. Before we dive in, Yash, you want to say hi to our listeners?
Hi, glad to be here talking about another interesting paper. We discussed this internally and we found it to be really valuable, and I'm glad to share insights with the community.
Yeah. So what is this paper? Like, essentially, what's the title? Who wrote it? Why did it catch your eye?
So paper's called TMax. That's the name of the data set that they release. The background here is it's created by AI2, Allen Institute for AI. It's one of the few organizations that are truly open AI, but also have the ability to train models and have the kind of compute for that. I believe like they were initially sourced by Paul Allen, one of the Microsoft co-founders. So they've been really helpful. It's one of the great places where PhD students want to go to if they want to actually train models and have the resources for it, but also put out their work and make it open. And it's an organization we've been following for a while because what they do is they not only put out papers, but also put out code bases, and they try to release all of their techniques. And the idea is very much in this open source movement of training frontier level amazing models should not just only be the domain of the Anthropics and the OpenAIs. That information should be disseminated widely. So that's the context. This paper was specifically looking at terminal agents. And so terminal agents here so first of all, agent. Agent is a language model with a harness around it. The harness is often tools. So if you ask Claude something about a current day event, you don't want it to just hallucinate something for you. You want it to use a web search tool to go and look some things up to make sure it has accurate information. That's an additional tool that would have, and you give it access to that tool. A terminal agent is a very minimal harness where you give the agent or the model only access to the terminal as a tool. So the terminal is essentially something that developers use on their computers in order to issue commands to essentially control a computer. So the idea here is that the minimal harness or the minimal tooling needed to do a wide variety of tasks is really just give the model access to the terminal. And if it has access to the terminal, it can do lots of things with it. So this has been very popular in the community. Because of that, benchmarks have come out around it, like scoring models and how good they are at using the terminal to solve tasks. And this paper was looking at, there's been, of course, lots of work, both by Anthropic and OpenAI, as well as some of the Chinese labs, in really trying to compete on these benchmarks. But even for like the Chinese labs, we have to define what open source means. They release their models and they might write up a paper, but they won't release their entire training recipe, enable you to exactly replicate what they're doing. So they're not what you could call their open model, but they're not open data. And that's often a classification here, and you would need their data in order to do it. So AI2 is open data. And so what they're showing here is that they can take some of these base open weight models and they've come up with a training recipe that they've completely open sourced. So anyone who, of course, has the resources can actually use that themselves in order to boost those open models' performance on terminal agent tasks.
So this paper, what is the topic at hand? What are they trying to solve for?
Yeah, so I guess maybe we should understand what terminal agents do. So it's very similar, I guess, I think we talked a bit about OpenClaw on our earlier podcast.
Yeah.
It's very similar to that. Actually, if you look at Terminal Bench, which is one of the most popular benchmarks for measuring terminal agents, it's a lot of that. It's a lot of, there's a lot of software engineering work, of course, because software engineers use the terminal all the time. Data analysts use the terminal. Security engineers use the terminal. And then also even OpenClaw style tasks of technically you can use the terminal to create calendar invites, for example. The terminal just gives you the ability to take actions on your computer. So technically, it might not be the most human easy way because there's no front end, there's no UI, there's no website. But technically, you could do really anything from the terminal. So in some sense, you could say a terminal agent is a really good terminal agent is a very capable agent at doing lots of things. And so their goal here was that current open models are okay, say, at terminal agent tasks, and we want them to be better. And so they came up with an open recipe, communicated that to community for improving those open models so that they're now competitive with the frontier. So, for example, a Qwen model might perform, let's say, 25% on terminal bench, but Claude Haiku, like a cheaper version of Anthropic's model, might score 33%. They're able to boost the Qwen model from like 25% to 31%. And a 6% improvement might not sound like much, but when you contextualize it there, this is the difference between a Qwen model versus an Anthropic model that might be relevant to you. But to be fair, like we can of course judge the results, like whether the results are significant or not. But the biggest advantage of this paper is the fact that they've completely released their entire recipe. And it's learnings for those like for example us, for example, or the rest of the community who are also training small models for what are the things they learned and what worked for them.
Yeah. What did they learn? What was surprising to you diving into that?
Yeah, lots of things there. So I guess maybe the first place to start, which is really in the name of TMax, is the data set. Because that was, I guess, their first decision. In order to train a model, we need data. Where am I going to get the data from? If I care only about terminal bench and I train only on terminal bench, it's probably only going to be good at terminal bench and then fail outside of it. And so this notion of generality is something challenging for any sort of model developer. Even if you're training task-specific SLMs, if that model doesn't generalize, at least within that task, then when you hand it off to users and users do anything new, the model will fail. So that was their first thing. Where do we get our data from? And we don't really want to train on terminal bench. We want to come up with a data set and test only on terminal bench so that the eval retains its sanity and it actually tests what we care about it testing. So I would say there's like two different avenues here for like collecting data for post-training, and they decided on one of them. Post-training meaning fine-tuning here. So fine-tuning existing model, not training from scratch, which is something which has been popularized by benchmarks like SweBench, which is take existing code that exists on the internet, for example, on GitHub, public repositories on GitHub, and use that to create data to train the models. So, for example, take a large GitHub repo that somebody has put out, an organization has put out. They have lots of GitHub issues which show all the problems, as well as lots of GitHub pull requests which show all of the fixes to those problems. And then also lots of unit tests, which are tests that are run to verify that these fixes actually do fix the problem, and therefore we can now trust that we want to import this pull request in the repository. So since you have all the information, SweBench, a benchmark which came out a few years ago, took that information to say, I'm going to ask a language model to do bug fixing on these software repos. I'm going to hand it as a prompt the GitHub issue, a real GitHub issue, and then I'm going to test it on these unit tests that already exist. And then I also know there's a correct answer to this because a pull request already exists for that. So I have all the elements needed in order to have a good database to train a model on. The challenge here is you are, of course, restricted to only repositories that exist on the internet. And therefore, you might not get the level of diversity you might want. And they did even see this in their experiments. So they did not go that direction. They instead went a direction which is really only enabled by the fact that frontier models are so capable today, which is as opposed to taking real repos that are written by humans and then adapting that to data, why not just ask Gemini to create everything, essentially? And that's essentially what they did. Their effort was in sourcing the prompts to Gemini for the repos and the tasks they like to create, the data they like to create. So they created a bunch of different axes, different personas, different programming languages, different types of work, and they just created a bunch of these axes, and they just take all combinations of this. So I want to take a security engineer that's really that's working at 3 a.m. on some security problem, and they're working in, pick a random programming language, C, for example, and they're doing, pick a random type of work, data analysis for whatever reason. And so then you get lots of different combinations. So that's what they did, and that becomes a prompt to Gemini, and they just ask Gemini, create a training example, create data out of it. So what Gemini did is like, I need to create an environment, I need to create a Docker container, I need to create an actual task, I need to create everything. And it seemed to work, which was, I think, pretty interesting to me, that these frontier models have gotten so capable that the synthetic data has gone to the point that you can just ask the model for what you want. You don't even have to seed it with anything real. And it can produce stuff, which helps. To be fair, they do call out on their limitations that because all of the data was created by Gemini, they don't expect this approach to get you to surpass Gemini, but that wasn't their goal. To be clear in this work, they just wanted to boost Qwen models or SLMs that you can actually run and just make them a bit better, not get to the true frontier.
Yeah, what's interesting there that I think about is a pragmatic approach that is commercially viable, because I know you're a fan of that, specifically generating high quality synthetic data for
Yeah,
practical use in a product. Like we do that.
absolutely. I guess indicates like we can be even more ambitious with our synthetic data generation. Like this kind of synthetic data generation is really agentic, you could say, that you're really
Mhm.
asking Gemini to basically create a whole environment, a whole problem, and it seems to do it well enough. And the validation is that when they train on this purely Gemini created data set, it actually improves the model's performance on real terminal tasks because they kept the test set truly a test set, and they made sure there was no contamination between whatever they trained on and whatever they tested on. It actually helped that Gemini data.
One aspect of the paper was around the data set difficulty, right? And what were they noticing there? What's the significance of the open data sets that are available and their difficulty level?
Yeah. So they were, I guess, what they were arguing is providing some statistics as to why their data set that they created should be used by the community, essentially. So you can, of course, say that maybe all this is unnecessary. All we care about is terminal bench performance. The fact that improved terminal bench performance is good enough for me. That's great. But they wanted to provide some additional statistics. So they looked at, you can say a lot of things, but we can reduce it down to two things. One is how hard is a data set for existing models? If the data set is really easy, for example, if like a Gemini model scores 92% on it, then arguably you can still boost small models on it because a small model might not perform 92% on it, but you have a lower ceiling, you can say, because you already know it's easy to a frontier model. So you're not giving it anything that's challenging to a frontier model. So you're kind of putting a ceiling on how good your SLM could be. So difficulty matters. You want to, if it's too difficult, maybe you don't get any, maybe the SLM isn't even able to train on it, but you want the just right level of difficulty. So one thing they showed there was that existing open data sets had like Gemini scored like 92% when treating that data set as a test. And in their case, Gemini scored about 40%. And they also did it in using a metric called pass at K. So all pass at K means is that if it's pass at 1, you give Gemini 1 shot to answer this. If it's pass at 8, you give Gemini 8 shots. And one thing they showed was that even if you give Gemini 8 shots, it still doesn't completely solve this TMax benchmark, which is also interesting. I believe they used a faster and smaller version of the Gemini model for these tests. It would be also interesting to look at, since a big Gemini model created the data set. If you were to ask the same big Gemini model to answer the data set, it's very possible the same Gemini model would score incorrectly on it. Because just because it was able to create this data doesn't mean it's reliably can solve the problems it's already created. So that was one thing. They validated that their data set was difficult, which is valuable because it means that the ceiling is higher if you train on that data set. And then the second thing they measured was how diverse the data is. And this, I think, was pretty striking because if we go back to what we were talking about earlier, that sort of adapting existing GitHub repos was popular by SweeBench. And SweeBench also has its own training set called SweeSmith. And SweeSmith was something they compared to there, especially on the diversity measure. And there's actually a few things to be said here. So you might imagine that because they asked Gemini to create everything, as opposed to using existing real world repos, then potentially that would cause some difference in the data set statistics versus the data sets you would get by adapting real world data sets, real world repositories. And it does come about. So really, when Gemini is creating all this data, it has to kind of create the repository from scratch, meaning just essentially write up a whole programming database, essentially, and then create issues and create tasks. So I don't know, they didn't absolutely come up with all of the details in the paper. It's very possible this is elsewhere, but you do want to kind of limit the amount of tokens you ask Gemini to use, or else you're going to go bankrupt trying to create this data set. So, unsurprisingly, the kinds of like code bases that were created for each of the tasks within TMax were smaller than the code bases you would get if you were to just take existing real-world repos, because these real-world repos are years old and so many human developers have worked on them. This also means that the number of turns, or like the number of tool calls a model needs to take, the how long the traces, like how long the model needs to work in order to solve the problems, is also shorter when it comes to TMax versus Sweetbench. So then you might argue, or Sweetsmith. So then you might argue that like it seems like this is worse. But the one place where they clearly went on also came from how they source the data. As we said before, when you take existing real-world repositories, you're limited by the existing real-world repositories that exist. So partly because of the bias that the Sweetbench papers, it's Sweet in the name, were very clearly biased by software engineering. And you can also argue most GitHub repositories are also software engineering. About 95% of the data sets that were for Sweetsmith, despite the fact that it seems like it potentially is longer or like more complex repositories, 95% of it is software engineering. Well, in their case, as we said, software engineering is only 1 out of 9 domains that they considered. And so given that, software engineering is only about 10% of their data set, and they had 10% machine learning, 10% security. So lots of diverse types of work. And this also makes sense as to why this would make sense for Terminal Bench. Because if you look at Terminal Bench, it isn't just software engineering. It's literally anything you can do with a terminal. So it's also that machine learning, security, scheduling, calendar invites. So it was a sensible approach for them, given they cared about terminal agents. And it also meant that they have diversity in their data set. The last thing to call out here, just because it's a nuance, is the way they identified that that 95% of Sweetsmith was software engineering was, again, taking a Gemini model, giving it those 9 domains that they already had curated before, and asking Gemini to go through Sweetsmith and classify each of these tasks into one of these domains. So it is also possible that 95% isn't actually 95%, but these frontier models are quite good. That it does seem, and also is it makes sense that Sweetsmith will be 95% software engineering.
Some other findings that I thought was surprising, maybe for our listeners, but not so much for ourselves. Like, we know this, but same technique, same data helps one model and hurts the next one, right? So there's no like one size fit all approach to this. And it's an open question. Like, they don't even address why, right?
Absolutely. That was very striking reading the paper. And it's actually a +1 to our thesis. So something we talk about a lot is that different models behave differently. And there really isn't a one size fits all approach, which means doing SLM creation really isn't easy. You might find one recipe which works in one scenario, it doesn't work in another scenario. And if you don't try the other scenario, you're leaving value on the table, essentially. So having an organization that really knows SLM creation and has all these recipes and knows how to do it is really valuable, because it's a very big sort of skill gap and lots of experiments you need to get your handle on this. And this paper also shows that. So on one hand, they really reduced themselves to only considering the Qwen models, the Chinese models. And we know that like lots of enterprises don't even want to consider the Chinese models. And so that is one constraint that they already made. And even within that constraint, they saw so many differences. So they took a bunch of Qwen 3.5, Qwen 3.6 models, different parameter sizes. But again, these are largely similar models. But one thing they found was that if they apply their same training approach, so specifically their supervised fine-tuning approach, to a Qwen 3.5 model versus, I believe, a Qwen 3.6 model, the same recipe improves performance for one of them, degrades performance for the other. And then they had to kind of just try to explain that by saying like, well, they were trained slightly differently, etc. But what this really means is that even models within the same family, and even like slight iteration on them, 3.5 to 3.6, they were trained differently. And really, a lot of this is there's a like mechanistic interpretability is a field for a reason. Like, we really don't understand a lot that goes into these sorts of models. So whatever changes Qwen made or Alibaba made, going from 3.5 to 3.6, they might have thought that was innocuous, but it could lead to different dynamics when it comes to those models that when you apply one training approach, it just doesn't work. And so it becomes very important to like for any kind of model you consider to really experiment with it, to really know its ins and outs, and to come up with recipes for it. And then that's what we kind of bake in to our SLM creator tool so that depending upon the model we consider, we're applying the right recipe for it. Because if you were to apply just a single recipe, which we saw very early on, if you apply a single recipe to every model, you're going to get variable results. You don't get reliability.
Right. And the commercial impact of that is that we notice with even our customers, many of them, when they first speak to us, are like, oh, I'm just going to have my smartest engineer go and fine tune some models and we're going to cut costs on this task ourselves. And so far with that exact conversation, we're 3 for 3 with customers who within weeks are like, hey, actually, we want you guys to handle this for us. And a few things like one example is they couldn't get GPT-4o, right, to perform better than 80% accuracy. And they were trying different approaches. And then they started to explore open models and fine tuning open models after that. And they just couldn't do it. And they're like, okay, you guys tackle that. And then we knocked it out the park. And other examples, you're chasing the next task and the next task, and it's whack-a-mole, and you're not getting a compound advantage, right? And so this is all we do. So fine-tuning models through the task-specific lens is really a craft, right? It's challenging. And that's what makes it fun. So another thing that was kind of stand out in the paper, surprising, is the model tried to cheat, right? You want to talk a little bit about that?
So we've seen this ourselves. They did call it out that like this was not, OpenAI's Hugging Face controversy of like really breaching into corporate code and like breaking things, or whatever was discussed about Fable 5 and like its cybersecurity exploits. Which again, like not to dismiss those, but like this was definitely not that. This was something we've seen day to day, where if you give a small model, for example, a very ambitious task, like for example, do my accounting for me, for example. But then within the harness, there's like 500 different tools, which again means that we can also talk about this. There's like some harness selection going on here where they found that a lightweight harness, mini sweet agent, outperformed a more complex harness, Terminus 2, by 5% when it came to Claude Haiku, which is the smallest Claude model. And this kind of harness choice does make sense because small models have limited context windows. And so if you give it too many tools or a very complex harness, you could just confuse it. And so getting the right recipe towards this harness really makes the most sense, and this training recipe makes the most sense, is a challenge. And it's something that, again, is not easy, which is why having expertise here matters. But anyway, going back to the harness point, let's say you're doing that accounting workflow and you have a very complex harness, or you don't even have a harness at all. And so you're essentially asking the small model, do my accounting for me, and it does not have the tools, or it doesn't understand the tools in order to actually solve the task. One thing you'll see the small model do is you're going to, especially if you let it reason, because the small models are capable of reasoning, they're thinking about it, they're like, I don't know what to do here, like I don't feel like I have the tools to do this. So they're like, oh, instead I'll just give them something to work with. And you even see this in OpenClaw cases where I don't think I have access to send this email. Let me give them a draft, for example. And they can send the email themselves. Let me do something. And so these are very common errors that you see when you're really trying to push the frontier. You're trying to get small models to do agentic tasks. They obviously saw some success here. We've seen some success there, but none of us are arguing this is easy. And when these models fail, they fail in very understandable ways where they just feel they're indicating in terms of their reasoning and what they're saying in terms of their thinking that they see this task as still beyond them, which is why continuing to push the frontier is super important.
Another thing, so Harbor, a framework for evaluating and improving agents. So in this paper, they call that out. They evaluated on Harbor. Is there anything to mention there? What is Harbor? Why Harbor? And, we also have some perspective there.
Harbor is something we're very familiar with. So it's something that we've been using to build up our internal database, because what Harbor essentially gives us is a framework for running agentic evaluations. So obviously we're in AI agents world. We moved past ChatGPT queries, question answering, and we want OpenClaw. We want Claude Code. We want agents to do work for us. This is where we're going. And a lot of the work that we do is that small models can do this as well, which means that we need to be able to put small models into a harness, make a small model agent, and actually evaluate it on real tasks, like Terminal Bench, for example, where you're asking it to do all these sorts of things. So that needs to be done. You need infrastructure to be able to actually run that. And Harbor provides that sort of framework. With that said, there's we can talk a bit about some of the internal tooling we're sort of building internally that to make this happen. Because while Harbor is getting very popular and lots of people that are looking at agentic tasks are using Harbor to run evals, there are still some things missing, which we're of course trying to work through and trying to contribute to in that way. So to talk about this paper in particular, for one, I think they're very familiar with Harbor as well. They're one of the many organizations that have adopted Harbor for their agentic evals. The AI2 team is very connected to the Open Thoughts team. The Open Thoughts team put out something called Task Trove, which is their version of running a bunch of Harbor tasks and providing this to the community. So they're very familiar with Harbor. To be clear, though, in their case, they ran Harbor and they used it to run agentic evals. They used it as infrastructure, but they only used it on 3 data sets. 3 well-specified benchmarks. Terminal Bench, I think 2 Terminal Bench variants and then a SWE Bench variant. Because again, these are the things that were relevant to them. They were looking at these real-world repositories and these coding agent style things. So it was totally fair for them to do that. And we've seen this time and time again, that especially when academic labs leverage Harbor, even outside of academic labs, they do the standard approach of evals where I care about these 3 data sets. I'm going to need to write code for these 3 data sets. And maybe the code that I use will use Harbor, for example. What we've been doing internally is we've been creating something called Harbor Master. And what Harbor Master is intended to do, which we've had some early success doing, but it's a hard problem and we're continuing to build on it, is not only run evals on a specified data sets that are already great and we already know are going to work, but instead be able to take any data set that can be put into the Harbor framework or the Harbor format and be able to run evals on them, which is a considerable infrastructure problem because when in an agentic world, you're creating an environment, you have to deal with Docker images, you have to deal with weirdness there. And lots of these data sets are just really not vetted and they're not sanity checked or they're not put through a hygiene cleanser. And so if you were to just do this naively, you're just going to have failure. And the failure is not due to the model. The failure is due to Docker image mismatch and just very low level infrastructure things. And so while of course we're also in the business of using the evals that actually exist and are well vetted and running things on them, because we're also interested in small models. And so they're not very interested in small models. So these are things that we can do. But one thing that we're building internally and some early successes we have are creating watchdogs, for example, and these kind of hygiene checkers. It's plumbing basically, so that when data sets come in, we can verify whether the data set can be run. We can patch the data set if it's not able to be run, so that we now get to a push button system leveraging Harbor where if we want to run any sort of eval, we can take some abstract business relevant task, find a relevant agentic eval for it, and then do that infrastructure plumbing, which to our understanding doesn't really exist because people are just assuming that this requires an engineer to actually work on this, do the infrastructure plumbing, make it scalable so that we can push button and do that automatically. We don't have to put an engineer on every particular eval to do that plumbing and spend human hours on it.
Yeah, so we regularly publish some of our findings on neurometric.substack.com. So you'll see us post about what we're learning, what we're doing, some of the large scale benchmark studies to evaluate AI agent performance. I mean, like, what was it, 6,000 benchmark runs at least and 15,000 individually graded tasks. And we're just publishing what we're learning and contributing to the community there. So check it out. We'll drop that in the show notes as well. Anything else in the paper that you wanted to talk about that really stood out to you, or any main takeaways for the audience?
So I think we touched on a lot of the main parts. The data set generation was their big contribution year. I mean, you need good data. One thing which they showed, which was interesting, is that because their data set generation was so focused on diversity, it really implied that arguably they post-trained the Qwen model to be even more general than it originally was, in the sense that they didn't just see gains on terminal bench, but they also saw gains on SWE bench, and they also saw gains on AMI, which is competition level math exams, where of course a coding agent can be helpful there because you can write code to like test sort of things, and see like whether your solution works. And they saw boosts across the board, which was interesting. And it also comes from the fact that they created a general recipe. It was also relevant, like when we, for example, work with customers and we see that they have a very general problem that they're tackling, then general data recipes and building a general model becomes very relevant. Well, of course, we want to make it as specific as possible because it cuts it down our costs. Sometimes generality is just necessary to satisfy a customer. Additional things would be, they did look at some like sort of technical things that we've also encountered, where agentic training is hard, you could say, and it means that you're training a model, especially if you do something called reinforcement learning. What you're doing is you're asking the model to solve the agentic task. You're seeing how well it does, and when it does something well, you tell it good, keep doing that. When it does something bad, you tell it not good. Right? That's essentially reinforcement learning. The challenge here is that when you're doing an agentic task, in order to just see whether the model did something right, you need to put in a harness, it needs to call some tools, it needs to do multiple turns, you need to get to the point where it gave an answer. It's all very expensive. And so there's a compute threshold there, which of course we've had to deal with. Like if you wanted to do it yourself, for example, the compute that's needed to do it is sizable, unless you really know how to kind of navigate around that and pick, for example, good small models so you can keep things within budget. And then secondly, because these agentic tasks can really be infinite in some sense, like infinite number of turns. You could say the agent did a tool call on one of its things, and that tool call was the wrong tool call. And it instead led to like a 50,000 word document being fed into the prompt. And then now the model is spending a bunch of time reading a 50,000 word document, and it's never ending. There's a ton of these problems. Sometimes that's unavoidable because the task is just hard. It requires, so there's both infrastructure and being able to prevent those failure modes, keep your compute within budget, and then also being able to manage that training so that you're training in a very hard scenario, but you can actually get something out of it. So they had a bunch of these sort of technical sort of tricks that they learned, tricks that they borrowed from some of the Chinese models when they put out their papers, for example. And some of these tricks we were already aware of, and some of these tricks we learned something from, which was definitely valuable. So yeah, the way I view this paper is it did a couple things. One, it validated the two things. One, it presented a recipe. And that recipe, I think, was valuable, and we definitely learned things from it, and we definitely validated some things that we're already doing internally based upon it. And then secondly, it also showed that when you really try to do this for real, and you're not advertising, for example, you're in academic labs, you're going to put out all of the results, you end up seeing something that we've been arguing forever, which is that this is hard. And if you train a Qwen 3.5 model, don't just imagine that like this is going to work on a Qwen 3.6 model, because it might not. There's a ton of expertise that's needed to do this at scale. And it's something where potentially it's a good investment to externalize that than committing the amount of resources you would need in order to become supreme experts in building small models.
Absolutely. So encourage everybody to check out the TMax paper. We'll drop links into the show notes. And if you like this episode, be sure to hit the like button, share it with a friend, subscribe, and thanks again for joining the Token Engineering Podcast.